Greetings, welcome to lesson 29. In this lesson, I'll go through a numerical example in which, using symmetrical components method, I'll find the currents through a balanced set of three impedances that are Y-connected and have a floating neutral point. I have another example of application of symmetrical components in lesson 28. And since originally I wanted to keep this example in that lesson as well, I'm going to still call it example 2. Notice that the load in this example is balanced with a per phase impedance of 30 plus J25 ohms. Two of the line-to-line voltages are given. Those are VAB and VBC. Using KCL, we can find the third line-to-line voltage, VCA. Starting from point A and going down to point B, there is a voltage drop of VAB. Going from B to C, there is another voltage drop of VBC. And going from point C back to point A, there is a third voltage drop of magnitude or a phasor value VCA. Adding those three together, then they have to come to zero according to KVL. Now in this equation, we have two of the three voltages, VAB and VBC. We can find VCA as the negative of the sum of the other two. And substituting for the values, we can find VCA as this value here. And summarizing the three voltages on a single line, we have all three here on the top line. For the rest of this solution, I'll find the symmetrical components of these three voltage phasors and apply each set separately to the load. The component currents are found in this way, and from component currents, each line current can be calculated, as will be explained in the upcoming slides. Let's find the A component of the zero sequence set first. I'm calling that VAB 0. The A component of the zero sequence set comes to 0 because we just saw that the sum of these three equals 0 based on that KVL that I just went over. This is true of any trio of phasors that add up to 0. Such trio will not have a zero sequence set. Line-to-line voltages of three-phase systems is one example, as we just saw here. Another example is the set of currents into a delta load. And another example is the set of currents into a floating Y-connected loads, such as the one here. For a delta load or for a floating Y load, the three currents coming in, IA, IB, and IC will have to add up to 0 according to KCL because they go across this boundary and there's no return current, so their sum has to add up to 0. That means that their zero component, the zero sequence set, will have components that are all identically zeros. Again, we are finding V0 here, but I'll keep the full index as VAB0 so that we can keep a better track of the components as they are being calculated. V1 or VAB1 is found next. This is the expression for it. As a reminder, the A is 1 with 120 degrees and A squared is 1 with negative 120 degrees, which means that multiplying any phasor by A will add 120 degrees to its phase angle, and multiplying any phasor by A squared will subtract 120 degrees from its phase angle. Substituting the values from the top line and doing the math, The answer for VAB1 comes to this number. And VAB2 is calculated based on this expression, and again, substituting for the values of the line-to-line voltages. The answer for that one comes to this value, 100 or 1146 volts, roughly, with negative 20.67 degrees of phase angle. Let me summarize the components that have been found so far. Here they are: VAB0, VAB1, and VAB2. Reasoning about the three components of the currents into the phase loads, it is clear that the zero sequence set of currents has to be identically zero due to the KCL, because their sum as they flow into the neutral point has to be zero, and since they are identical to each other, then they each have to be zero. You have three numbers going in as IA and IB, well, IA 0, I should say, and IB 0, which is again equal to IA 0 because it's part of the zero sequence set, and IB 0, which is again equal to IA 0. So three of them adding to 0, 3IA 0, equals 0. So IA 0 has to be 0. Again, due to KCL, because they're going across the boundary here. And for the floating neutral case of the Y-connected load, there is no return line. There is no neutral. So the sum of the three currents has to be 0. Let's look at the positive sequence component VAB1, which along with VBC1 and VCA1 form a positive sequence set. We do not need to show or calculate the positive sequence components VBC1 or VCA1 because both the load and the sequence voltages are symmetrical. All we need to do is find the positive sequence component of line to neutral voltage VAN1, and from it the positive sequence component of the line current IA1 can be calculated. Remembering that the relationship between the line to line and line to neutral voltage is of a balanced Y-connected load with balanced positive sequence voltages, VAN is calculated as VAB over square root of 3, and it lags the phase angle of VAB by 30 degrees. Calculating that, VAN1 comes to 2602.7 with 3.11 degrees. Next, I'll use the negative sequence component VAB2, and from it, I'll find the VAN2. VAN2 equals VAB2 from here, divided by square root of 3, but because it's a negative sequence set, the phase angle for the line to neutral voltage leads the phase angle for the line to line voltage. I've drawn a second diagram here. The top one shows the load with positive sequence voltages and currents. The bottom diagram shows it with the negative sequence set of voltages and currents. VAN2 is found from this equation, and that comes to 661.74 volts with 9.33 degrees of phase angle. So here they are, all of the A components, VAN0, VAN1, VAN2, all A components of the line to neutral voltages. Ignoring the VAN0 as it does not generate a current in any of the phases, the A components of the positive and negative sequence currents are easily found using Ohm's law. So IA1 would be VAN1 over Z, and that comes to this current. And IA2 is calculated as VAN2 over Z, and that comes to this value. Here it is. Here are the positive and negative A components of the current. Because of the symmetry of the load and of the currents, the other two components of the current for each of the two sets can easily be found by shifting the phase angles appropriately. So from IA1, if I subtract 120 degrees from its phase angle, it will give me the phase angle for IB1. The magnitude will stay the same, of course. And if I add 120 degrees to the phase angle for IA1, I'll get the phase angle for IC1. And that forms the positive sequence set. For the negative sequence set, I'll do the opposite. Here, IB2 leads IA2 by 120 degrees, so I'll add 120 to this phase angle to get the phase angle for IB2, and I'll subtract 120 from this phase angle to get the phase angle for IC2, and that's because this line belongs to the negative sequence set. I would be adding I'm going to add the components of each phase, the components of the currents for each phase, the zero and positive and negative sequence components. The zero sequence component of the set is 0, so I don't need to add that. I'll just add the positive sequence and negative sequence components for phase A to get IA. I'll do the same thing for phase B to get IB, and similarly for phase C to get IC. Okay, so if you substitute for IA1 and IA2 from here, you get this for IA. Substitute in this equation for IB1 and IB2, you get this value for IB. If you substitute for IC1 and IC2 from here into this equation, you get the value of IC, and here are all three currents. Note that even though the load is balanced, the currents are not, because the voltages were not balanced. As an exercise, I'm going to suggest another way to solve this problem. You can convert the load into its equivalent delta load. Just remember that the delta load, the impedance of each phase of the delta load is 3 times the impedance of each phase of the Y load, if they are to be equivalent. And then we can find the phase currents by dividing each line current by each of these impedances. For IAB, going in the direction of A to B, VAB over 3Z. For IBC, this one, going from B to C, we'll divide VBC by 3Z, and finally ICA is found by dividing VCA over 3Z. Once we have the phase currents, we can subtract them 2 at a time, as shown here, and that will give us the IA, IB, and IC. And I haven't done the math for these, but the answers, if it's done correctly, should come to exactly what we found earlier, using the symmetrical components. So that would be a good check on those results. Although for this example, the application of symmetrical components has led to a longer solution than what has been suggested on this page. However, the symmetrical components method proves its value when applied to very complex power systems in unbalanced operation, as it separates the system into 3 separate but related sequence networks and applies sequence voltages or currents to each and collects the results to determine vital parameters such as short circuit currents, over voltages, etc., which are all useful information in fault analysis and design of protective systems. We have reached the end of lesson 29. My name is Fuad Albandi. I am a PE in electrical power engineering. You'll find my name, web address, and email address on this page. My web address is own-your-destiny.mylearnworlds.com. Email address own-spelled out, your-spelled out, destiny@yahoo.com. I invite you to visit my website when you have the time. You'll find comprehensive modules on different topics of power systems engineering on that website. Thanks for watching this video, and I hope to see you soon in another one of my presentations.